Question 6a. A conical pendulum consists of a light and elastic string PQ at the end P with paragon attached to the other end Q. The paragon moves uniformly in a horizontal circle whose centre 0 is vertically below P. If OP or PO in terms of H. Okay, so what we're going to do here, just give me 1 second. Alright, that doesn't work. So, okay, so what we're going to do is we're going to draw a diagram of this pendulum consists of. So it's basically the pendulum is rotating around in a circle, okay, from a string that's attached at a point P. So what we're going to do is we're going to draw our two-dimensional diagram, probably starting off. Okay, so we have our, this is what we have here, and then we have an ellipse. The ellipse is located here, and that's roughly it there. Okay, so this is our system here at the moment. Okay, 2005. Okay, so there's T, which is the tension of the string going upwards. The mass of the particle going directly downwards at point Q is mg, and then we have the height h. Okay, let this angle here be the angle theta. Okay, and it really doesn't matter if you put theta here or theta up here. It really doesn't matter. You just set up. It just changes sine with cos. Same system. Okay, so we're going to do we're going to also do Pythagoras' theorem on the triangle, and we're going to figure out what is the this length here. Okay, so what we can do here is this is h, this is the radius of the motion, and therefore by Pythagoras' theorem this length x is x squared equals h squared plus r squared. X equals the square root of h squared plus r squared. So this here is h squared plus r squared. Now you might ask me, why did I do that? Well, it makes sure that the hypotenuse, and we're going to be using it for sine and cos, it makes sure it's in terms of h and r. Okay, so that's very important. So two main formulas when you're doing these questions. The main formulas is what goes up equals what goes down. So the tension T has two components. It has components going up, okay, and then it has components going inwards on the motion. So it's going to be, and this is theta, so this is going to be T sine theta and T cos theta. Okay, so going upwards we have what goes up equals what goes down is the first equation usually. Okay, so basically statics. Okay, so what we're going to have is T sine theta, which is the component tension going upwards, equals mg going downwards. Okay, that's equation 1. Equation 2 is basically what's going inwards, right? It's the centripetal acceleration. Okay, now we have a choice of which one we use. We can use mrw squared or mv squared over r. We need to use the available information to make a choice. Period of the motion. Period of the motion. That has made my call for me, hasn't it? I'll tell you why. The period is 2 pi over omega. That means we're going to be definitely using the angular velocity. Okay, so we're going to have a T cos theta, which is going directly to the left, as seen here, equals m or w squared, which is also going to the left because that's the sum of all the force going into the center. Okay, so now we have our two equations. Okay, now what's thinking we could do here is we could do a number of things, I suppose. What'd be really handy is, do you know why it wants it in terms of h? Okay, if we divide equation 1 by equation 2, what happens? Equation 1 divided by equation 2, what will happen then? The t's will cancel. We'll get sine theta over cos theta, which is tan theta. We'll get g over rw squared. And what is tan according to our triangle? Tan theta is h over r. So tan theta equals h over r, which is equal to g over rw squared. The r's will cancel, and we basically get h equals g over w squared. We want to get the angular velocity. Because we want to get the period in terms of h, we need to isolate the angular velocity. Okay? So the angular velocity, therefore, when we cross multiply upwards, angular velocity squared equals g over h. Angular velocity equals the square root of g over h. Okay? Now, period equals 2 pi over omega. Period therefore equals 2 pi divided by root g over root h. We can bring it up, turn it upside down, and we get 2 pi root h over g, and that's our answer there. Okay? Alright guys. Yes. This one here, a light elastic string of natural length A and elastic constant K is fixed at one end of a point O on a smooth horizontal table. Mass M is attached to the other end of the string. Initially the particle is held at rest on the table a distance 2a from 0 and is then released. Smooth horizontal table means there's no friction. So we're going to draw our table here. Okay, once we've drawn our table, next going to draw is our point O, and then elastic the particle M all the way at the ends. Okay. Now this is M. It's a distance 2a away. The string's natural length is A. Now, what does that mean? Quick note: the force that it's experiencing back inside is completely down to the extension. Do you understand? So remember that force is equal to, and the tension in the string is in the opposite direction because it's in the opposite direction to the extension. Okay, this means that force, which is MA, equals minus kx. Now guys, what does x mean? X is the extension from the equilibrium point. Now because this is a horizontal question, okay, and not a vertical question, the equilibrium point is located here at the natural length, because this is the point at which it has no extension and there's nothing pulling it backwards. Okay, so what we're going to get is MA equals minus KX. Isolate A on its own, equals minus K over M times X. Now, please remember this is undergoing simple harmonic motion. Okay? So it goes, particle mass M is attached to the string. Initially the particle is held at rest at table 2a from 0. Show that the time taken for the particle to reach O is this here. So we're talking about fixed at one end to a point O on a smooth horizontal table. So this is O here, isn't it? Yeah? So that's origin O. Now here's what's going to happen. The particle is going to experience an acceleration up to this point here. It will undergo simple harmonic motion in between these two red dots. The minute it passes out the middle red dot, it will then undergo just regular linear velocity with an acceleration of 0. So we're first going to get here to here. We're going to find out the velocity at this point here, and then we're going to see how much longer it takes to go all the way to O. So we're going to work off our linear velocity first, or our simple harmonic motion first. Please remember, A equals minus W squared X. or minus omega squared x. Okay, this is the formula for all simple harmonic motion. Compare both formulas to each other. This means k over m equals w squared. W squared equals k over m. Therefore, omega equals the square root of k over m. Okay? Amplitude of the motion. The amplitude of the motion is how far you pull it away from the equilibrium point. So what is the amplitude of this motion, guys? Amplitude equals small a. Okay? And velocity. Okay? We're now going to find out what velocity is. Velocity. Now, this is a maximum velocity, WA. Can anybody tell me where does that formula come from? It's not in your notes. It's not in the log tables. Alright, so you get your regular velocity. Now what's the formula for regular velocity? V squared equals? V squared by amplitude squared minus displacement squared. Okay, amplitude squared minus displacement squared. At your fastest point in the middle, yeah? At your fastest point in the middle, what we got to do is we got to find out what is the speed at this point here. And what you got to remember is there's no extension at this point in time, which means that x equals 0. And this means that v squared equals w squared, amplitude squared, square root both sides, equals w a. You either need to memorize off the formula or you need to know how to get there. Okay? So the velocity at the point A, or the maximum velocity, is going to be root k over m times A. So A times root k over m is the maximum velocity. We now know the velocity it's going at this point here. What we need to know is how much time it takes to get from here to here. How much time does it take to go in between the two red dots? Now, remember, the period is when you go, if this was obeying simple harmonic motion on both sides, the period takes to here, back to here, back to here. 4 equal slots. So this time equals the period divided by 4. Let's find out what the period is. The period is, formula for period, which is in your tables, is 2 pi over omega. This is 2 pi over root k over m, which ends up in turn to be 2 pi root m over k when you turn it upside down. Okay? Now we know what the period is. We now need to figure out what t is. T is going to be a quarter of the period, as discussed earlier. And a quarter of the period is going to be pi over 2 root m over k. Alright? When you go back up to the top, your velocity here we have. It now has to travel a distance a to get back to O. So remember, it's undergoing linear motion. Okay? So distance, time equals distance over speed, or distance over velocity. In this case, its distance is a, and it's going to be divided by the speed we got earlier, which is a root k over m. The a's will cancel. We'll turn that square root sign upside down, and it's going to be root m over k. Alright? Because there's no acceleration involved. So the total time is going to be this one here, t1, and this one here, which is t2. Add them together, and we get t1 plus t2 is the total time, and that will give me pi over 2 root m over k plus root m over k. I suppose I can factorise it out. Root m over k into 1 plus pi over 2. And that's what I was asked to prove, right? 2005? Yeah. Okay, guys.